Hello, Year 9. Here we go today. We've completed the work on forces and how they can be resolved and the resolution of forces. We're now going to move on to speed, distance, time graphs. Today we have got four learning outcomes. You'll notice that the bottom one is only for those doing higher tier. However, I think it's always good that everybody has a go at this because actually we should all be reaching for the stars. So, thank you for all the feedback from yesterday. Thank you for people that email questions. Please keep them coming. I'm here, I'm available, I'm ready, waiting, poised at my email if you need some support. Okay, let's move on. So I have attached this as a separate slide for you if any of you wanted to print this off. So this is the rag sheet that goes with this unit, and it would be good for you to evaluate your progress. We're not able to tell you at the moment how you're doing, so you can give your grade for before, red, amber, green. How confident do you feel at each of those? As I've said, I've attached this as a separate slide. Okay, be good to put in your books. All right, thanks. So 1 to 6 in your margin for me. We've got a quick quiz. Pause the slide and answer the following 6 questions. So displacement. Yes, it is a vector because it has distance in a given direction. Okay. How do you calculate the resultant force in a single force that has the same effect in all forces being acted on an object? What are the key conditions for an object to be in an equilibrium state? The resultant force is 0 and the forces acting on the object have no overall turning effect. What is the equation for linking speed, distance, time? Speed equals distance divided by time. 5. What is the meaning of parallelogram forces? It's a scale diagram of two force vectors used to find the resultant forces that do not act upon the same line. Number 6. Forces can either be contact or non-contact forces. Give the name of one contact force and one non-contact force. And I've just given you some examples here. But if you go back to your notes from lesson 8.1, you'll have those written down. So good stuff. So today we're going to be looking at speed, distance, time graphs. And first of all, we're going to go through speed a bit. And today I'm really excited because we have got an equation triangle. Yes, for those of you who've been listening to me whittering on about these for a couple of weeks now, I'm very excited by this. So speed equals distance travelled divided by time taken. And the units here are meters per second. Time is measured in, distance is measured in meters and time is measured in seconds. We often use the term kilometers per hour, okay? And therefore they're expecting you to know a couple of things. They're expecting you to times up. They expect you to know that there are 60 seconds in a minute and 60 minutes in an hour. Okay, to work out the hour, we do times 60 to work out the number of seconds. And kilometers, that means kilo is the prefix for 1,000. So that means there is 1,000 meters. Okay. Now, ta-da! Equation triangle, exciting stuff. So at the top of my triangle, I have distance, speed, time. Now, whichever one you're expecting to try and find out, you literally put your finger over and then you are given the equation for what you want to find out. So if you want to find out speed, which I've already got there, so it's probably a rubbish example, but I put my finger over speed and I've got distance divided by time. If I wanted to work out the time taken, and I put my finger over time, and then I've got distance divided by speed. And if I wanted to work out distance, I'd put my finger over distance and I'd do speed times time. It's exciting. However, when you've got an equation that's set up like this, you can always pop it into a triangle, and that is a simple way of rearranging it. I'm very excited by this triangle, sorry. Okay, let's move on. So some typical speeds for walking, running and cycling. Now, Miss Callis made this slide, so you'll notice that she has flipped units halfway through, and we've got running is 8.3 meters per hour, and then cycling is 15 to 16 meters per hour. Okay, so it's quite difficult to compare, but essentially, you've got to think about this. You can't make your units too unrealistic, otherwise they're going to think you're a lunatic and have spent far too long playing on your Xbox. So how do we calculate speed? Again, we've got another one here. We've got 46 miles being travelled over 2 hours, which gives me 23 miles per hour. So at times the car may be travelling faster or slower, okay, but that is the average speed. I might have stopped at some traffic lights, okay? It might have gone a bit faster because it was a nice clear stretch of road, and it might have been a short section of higher limit road. However, the average speed is the speed for that period of time. Okay, so one of the things we're going to ask you to do is pause the slide, answer the questions 1 to 3. Number 4 is a little mini practical for you to try. Please make sure you've got a nice open space to work this out. Right, so here we go. Usain Bolt ran 10 metres in 9.8 seconds. What is his average speed? We literally need to do speed equals distance times time divided by time. So that gives me 100 divided by 9.8, giving me a total of 10.43. Number 2, a dog runs at a speed of 5 metres per second. How far does he run? So we're going to need to rearrange that triangle to work out, make distance and manipulate it. So distance is the desired quantity. So we need to do speed times time. And that gives me 5 times 60, because obviously there are 60 seconds in a minute. The car travels at 30 kilometres and covers a distance of 900 kilometres. How long did it take? And you do 90 divided by 30, gives me 30 hours. And then how long does it take for you to hop 5 metres? That was just one for you to work out. So distance time graphs. Now, again, this would be a good point to try and do it with a ruler. However, side of your phone is fine. We don't actually need physical measurements. A graph can be used to illustrate the movement of an object over distance and period of time. So we often get asked in an exam, what is this graph showing? This is a distance time graph, okay? Different to a speed graph, different to a velocity graph. This is a distance time graph. And this section of the course, we are going to be looking quite a bit at graphs, and it's really important that you distinguish between these 3 different types of graphs that we need to know. So we've color coded it down the side for you. So here we've got this idea of gradients, so how steep the line is. And on a distance time graph, if the line is horizontal, completely flat, there is no incline in it or decline in it at all, then we know that the object is stationary. It's not moving. All right. And so we've got these 3 lines and 2 lines for 2 different objects. Now you can see that the blue line travelled 10 metres in 2 seconds. It's got a very steep gradient, so you can, from this, you can work out its speed. So you could go 10 metres divided by 2 gives me a speed of 5 metres per second. However, if I was to look at the red line, it actually moves 8 metres in 4 seconds. So I could calculate the speed by doing 8 divided by 4, giving me a speed of 2. Sorry, early morning, brain's not functioning. Now, if we actually look at the deceleration that's happening here at the end, we can see that, again, it's travelled another 8 metres, but this time over 3 seconds. So we can see that it is a little bit faster than it accelerated at the beginning, okay? So if we look at these 6 graphs, okay, think about the graphs and think about what each graph is showing. Just sketch out the 6 graphs, pause the slide, and then underneath say whether you think they're accelerating, stationary, okay? So think what you think the line, the gradient on each graph is demonstrating. I'll put up the answers in a second. So first graph, it shows that it is moving at constant speed. Second graph is constant speed, constant faster speed. So again, we're using that statement to show a difference between the two graphs. Constant slower speed, okay, and then graph 4 shows me that the object is not moving, and graph 5 shows me that the object is coming closer, and graph 6 shows me that the object is accelerating. So sketch graph to show this description. Think about what it's saying in the words. A car sets off at a slow constant speed and it stops briefly to refuel before setting off at a faster speed until it reaches its destination. It stops for a while before it returns home at a constant speed. Sketch out what you think that graph looks like. Pause the slide. And I'm going to show you the answer. So first of all, it starts off at a slow constant speed. So the gradient isn't too steep. Then it stops for petrol, so therefore we have a nice horizontal plateau. Okay, and then we have a faster speed, so it has to be a steeper gradient than we originally had. And then it stops for a while. Okay, it plateaus again. Then it returns home as constant speed. Now this needs to be one continuous line. And because there's no comparison to the first two types of speed, it doesn't matter how steep that line is. Okay, how did you do? So now we're going to have a go interpreting some graphs. And these questions are usually worth quite a bit in an exam, and they're often worth like 4 marks. And what I would do if it was me is I would break up the graph into sections, and that's what they've done in this question to talk you through it. So they've broken up the graph into 6 points, and they're asking you to comment specifically on each 6 point. Now, if you do that in the exam, then you've covered the whole of the graph and you've explained exactly what's happening. And you can do it in a logical order and fashion and show that you've worked your way through the graph and then nothing gets left out. So, distance time graph below represents a car journey from Barnsley to Nottingham. Again, they're going to use places you might never heard of, okay? Don't panic about that. It's not a geography test. They're just 2 places. A distance of 50 kilometres back again. What can you say about points B, C and D? So, B, C and D, what could we say? From the graph here, after 20 minutes, the car was at 16 kilometres away from Barnsley. Okay, nice big fact. After 30 minutes, it was 35 kilometres away from Barnsley. And after 50 minutes, the car was 50 kilometres away from Barnsley. So it was at Nottingham. It had reached its destination. You can see that the speed is different between each of those points. Next question, what can you say about the journey from D to F? Well, think about this. D, we're at Barnsley, okay? We're stationary between D and E. So let's see what they say. So between D and F, the car stayed at Nottingham for 20 minutes and then took 60 minutes for the return journey. That's all they want to say. Can you see here that A, I'm referring to the points on the graph, and B, that I'm taking measurements? If they're giving you the graph, it's really important to reinforce your answers, especially on the higher paper, with data from the graph. Don't go data crazy, but show that you are able to read that graph. It's there, use it, get those points. You can do it. C, work out the average speed for each of the 5 stages. So, A to B, 16 kilometres in 20, so you do 16, 20 minutes. Oh, I don't know. This is how Miss has done it. So, yeah. Not how I would have done it, but there you are. Alright. Okay, there's your answers. So, I've talked about the gradient quite a bit, so apologies if this is just reinforcing what you already know. However, the gradient is the line in the distance diagram equals the speed. So, what is the speed of an object between A and B? We draw a triangle, and we then work out the side of that triangle. So the object has moved 60 metres, because we do 70 take away 10, and it took 3 seconds. Therefore, we do 60 divided by 3 gives me 20 metres per second. Okay, so rules. There are some rules when we're working a distance time graph. What I'd like you to do is match up the rules to the meanings on the other side. Just pause the slide and have a go at doing this now for me. Right, so the gradient line gives the speed at that instant. If the line is parallel to the x-axis, then the speed is 0. The gradient is increasing, the speed is increasing. If the gradient is decreasing, the speed is decreasing. If the gradient is negative, the object is moving backwards. Okay? So, pause this, try and work out the values from the table below. So, here we go. B to C, 10 metres, 3, velocity of -3 because it's going back. C to D, 0 because it's stationary, therefore 0 divided by 2 is 0. -30 divided by 4 gives me -7.5. 40 divided by 4 gives me 10. Just simple maths. And you would have found yourself getting 4 out of 80, so 5% of the paper have been able to complete that table. It's easy marks. Look, don't leave it blank. So, here's Adam in a balloon at the county fair. Again, all a bit biff and chip, but here we are. They're having a race. They've tethered the hot air balloon. Again, some people are going, what the hell does that mean? It means they've tied it. The graph below shows the balloon at the height of the ground during part of their trip. Oh, text message. So, have a go at doing questions A, B, and C. Okay? And we'll go through the answers. So, A, how far the balloon went, 12 metres. Speed, 12 divided by 4 equals 3. C, 12 divided by 8 equals 1.5. They tend to be really nice round numbers, especially on the foundation paper, because they accept some people would want to do this in their head. However, if you're not 100% convinced of your maths, you are able to just put your hand up and ask for a calculator. No shame in it. You're a bit of an idiot if you don't, because they're there. Mrs. Thornwell loves handing stuff out. So key points. These are the definitions that you have to have mastered. Speed, acceleration, deceleration, and velocity. Okay, write these down. You need to know them. Okay, there is a SAM learning task associated with this video, so please can you do that for me today?